Hi, Sugar Plums. Happy October. Today we're going to start Unit 5, and we're going to start by talking about 4 theorems. So by the end of calculus, you're going to have 7 big theorems that we talk about. Um, so doing 4 today seems like a lot, but we're actually only going to do 2 of the 4, and maybe then only one of those 2. So the first theorem that you need to know is the intermediate value theorem. I don't teach this because Pickle taught it to you. So the intermediate value theorem is the theorem that says if you have a point here and you have a point here, then to get between points, you have to go through every point in between if your function is continuous. So this has a continuity condition built into it. So if you have a continuous function, then you have to pass through every point between A and B. That's all it is. You did it with Pickle. And when you did it with Pickle, you focused on, let me move this because I can. You focused on the points between A and B, one above and one below the axis. So you were proving that there were zeros in your polynomials because you got a value that was negative, a value less than 0, and a value greater than 0, so it had to go through 0. So that's how you used it. In calculus, you'll use it, but it doesn't have to go through 0. 0 isn't arbitrary. Your next theorem doesn't have a name, so it gets forgotten a lot when I ask you to list your 7, but it's very simple. If a function is differentiable, then that function is also continuous. That's it. If a function is differentiable, then it's continuous. So it's very simple, very straightforward. We can talk about the whys, but the big thing I want to talk about is how easy these are to switch, and you can't switch them. That's a big no-no. No switching. How come? Can you think of a counterexample to if a function, if continuous, then differentiable? Are all continuous functions differentiable? I mean, obviously the answer is no because I just said no. But the one I like to think about when I'm trying to remember which way this if-then statement goes is just absolute value. Absolute value is continuous. I don't have to pick up my pencil to draw it, but it is not differentiable at that corner. So that's how I remember which way that if-then statement is. Okay, now to the main event. Number 3 is Rolle's theorem. Rolle's theorem has 3 conditions that you have to meet. So if, and we're going to write them all out, and we're going to write them out properly. Here we go. If a function f of x is, let's do this one first, continuous on AB. So closed interval between A and B, it's continuous. That's condition 1. If it is differentiable on an open interval AB, we can talk about why that one's open and that one's closed, but let me write the last one. And if f of A equals f of B. Okay, here's the reason. So you're continuous from endpoint to endpoint. That means you need closed circles as your endpoints. But the reason differentiable is an open interval is simply because you can't take a derivative at an endpoint. Remember that a derivative is a limit. I'm sure you're all nodding eagerly right now, like you haven't forgotten everything we've done over these last 2 weeks. But a derivative is a limit, which means it can't exist at an endpoint because limits have to come from both directions, and an endpoint doesn't have 2 directions. Okay, so I'm going to draw a squiggle wiggle that meets all 3 of those conditions, and then we'll do the then statement. So I'll put A over here and B over here because I feel like it. Well, I have to draw a continuous differentiable function whose endpoints match. So f of A I'll put up here, and that means f of B also has to be here. So I have to get from point to point any way I want, as long as I don't pick up my pencil and I don't draw a cusp, a corner, or go vertical. So I'm just going to draw a simple squiggle wiggle because I'm still on break. So if those things, then At some point, here's your big takeaway, at some point between A and B, f prime of C, a new x value, has to equal 0 somewhere. So for some, I'll do it this way, for some C between A and B. Okay, so your derivative has to equal 0. What does that mean? It means visually, between A and B, you have to level off somewhere. That's not necessarily a max or min. In this case, it is because I drew something boring. But it looks like I have two values. So it looks like I level off here, and it looks like I level off here, and these are slopes of 0. They go horizontal, so I'll call this one C1. I'll call this one C2. And that's it. That's Rolle's theorem. So at some point, the derivative has to equal 0 because you start and stop at the same place. Okay, mean value is number 4. Mean value theorem. Whoa, CEO, nope. You know what? I'm still on break. I'm going to abbreviate it. Theorem. This one only has 2 conditions. If f of x is continuous on the closed interval a to b, and if f of x is differentiable on the open interval a to b, just like with Rolle's theorem, identical to Rolle's theorem. Closed means it has endpoints. Differentiable on open because you can't take derivatives at the endpoints. So you have a lot more freedom with your squiggle wiggle that you choose to draw in your notes right now. Here's A, here's B. Draw any squiggle wiggle you want because this one doesn't have the restriction of f of A equaling f of B like Rolle's theorem does. So I'm going to put this one here and this one up here, and I'm going to squiggle wiggle my way to there. Whoa, that's awkward. I'm going to try again. I'm just, you know what, I'm still on break. There, squiggle wiggled. I did it. I did it. Okay, this one. Then, this one's a little bit more involved, but I'm going to write it and then talk about it because I want you to see it while I'm talking about it. Just like with Rolle's theorem, this is all about there exists, you know that means there exists some C between A and B, oops, such that f prime of C, so the derivative at this magical x value that we haven't talked about yet, this time instead of equaling 0, it equals this. What? That's so weird. I've never seen that before. Of course you have, child. This is your calculus slope. This is your algebra slope. So when I ask you what is mean value theorem, I want 5 words from you. I want calculus slope equals algebra slope. That's what I want you to say to me every time. Calculus slope equals algebra slope. All right, visually, here's what it means. So we have to find this C value, which means I'm going to start with this side of your equation. That's an algebra slope between 2 points. Algebra slope needs 2 points. The 2 points are your endpoints, f of A and f of B. So they're talking about the slope of this secant line. And they're saying that somewhere on that curvy that I drew, my calculus slope, my tangent slope is going to be the same. So what it means to have same slopes is that it's going to be parallel. Oh my gosh. So 1, 2, 3, 4. I think I have 5 because I drew such a weird squiggle. I think I have one here. I think I have one here. 3, 4, and 5. And I could come down here and mark one as C1, C2, C3, but I don't care. That's mean value theorem. I want to, like a real world example of mean value theorem. If you're traveling along a highway and the speed limit is a happy little 50 miles per hour, and at 2 o'clock, I don't know why I'm making this so hard. I'm going to say it differently. After an hour, you've traveled 60 miles. So 1 hour, you went 60 miles. that means you were speeding. That doesn't mean you were always speeding, but it does mean that at some point in that hour, you were above the speed limit of 50 miles per hour. That's mean value theorem. So there are actually toll bridges and toll roads, like in Jersey, where everything's weird, that they clock you when you get on the toll and they clock you when you get off, and they apply mean value theorem to it. And if you travel farther than you should have in the amount of time that you had, you get ticketed. And it's all mean value theorem. And so that's what this is, because it's a derivative of a position is your velocity. All right, that was pretty rambling. Sorry. Happy break. Bye.